All right, everybody. Last video for this unit on equilibrium. Last time you're going to have to listen to me talk about reversible reactions, at least for the time being. Today we're going to look at buffers. You've probably heard of buffers before. We're going to go through the definition of buffers and then some calculations involving buffers. And hopefully this is going to turn out to be not too bad for you. So let's go through the definitions and the examples and see where it takes us. So to start off, what is a buffer? A buffer has to have a solution that contains a weak acid and one of its salts, or a weak base and one of its salts. It's able to neutralize acids and bases without allowing the pH of the solution to change a lot. So basically the whole point of a buffer is it resists changes to pH. So you can add acid and the pH might go down a bit, but not much. Or you can add base and the pH might rise a little bit, but again, not by much. So here are some examples of the pairs which make up buffer solutions. So they're shown in the table. So if you've got an acetic acid, a good example of a salt is sodium acetate. So again, we've got that acetate ion in both of them there. Phosphoric acid and potassium phosphate, oxalic acid and lithium oxalate, carbonic acid and sodium carbonate. All a bunch of examples. For the most part, you won't need to figure that part out. I will give you the buffer with the acid in its salt or the base in its salt, and you'll have to go through and actually do some calculations. So here is a buffer solution. Here is why it works. We're going to go through this quickly, and then we're going to talk about what actually happens during a calculation. So a typical buffer solution contains acetic acid and its salt sodium acetate. So we're going to go through this example. So if you have acetic acid, here it is right here, you know that it's a weak acid. So this here is a weak acid. If it's a weak acid, that means it will not dissociate very much, and most of the acid remains in this form because it's a weak acid. So the concentration of that ion or that compound is very high because, again, it doesn't dissociate. If you have sodium acetate, which is NaCH3COO minus, or sorry, not minus, just COO, you know that because it's a salt, it will dissociate completely into its two ions. So the concentration that we get from there is that. So because you have a weak acid and a salt, the concentrations of both of those entities are high. What does that mean? Okay, why is that important? Well, let's look at two scenarios. If we have this solution and we add acid to it, it's going to react with the acetate ion. Okay, so here's your acid reacting with the acetate ion and donating a proton, making water, which is neutral, and again this acetic acid, which is a weak acid, and it's not going to affect the pH very much. So that's why the buffer solution works when you add acid. If you add base, base is going to react with the acetic acid. So your hydroxide is going to take the take the H from the acetic acid. You're going to make an acetate ion and water. And again, both of these compounds are neutral, or fairly neutral. So again, if you add base, you're not going to change the pH by much. If you add acid, you're not going to change the pH by much. And that's because of what is present in the buffer. All right, so what ends up happening in these buffer solutions, we always have these equilibrium shifts as predicted by Le Chatelier's principle. We have to keep that in mind when we're doing these calculations because that will dictate which concentrations increase and which concentrations decrease. So, oh shoot, I didn't mean to have all this writing up here for you. I'm just going to erase it quickly. Oh, ignore all that. So, let's look at this example. What is the pH of a solution that contains 0.3 molar ammonia and 0.15 molar ammonium nitrate? The Kb for ammonia is 1.8 times 10 to the negative 5. So I looked that up in the back of the text for you. So here's the buffer solution, and you have two different parts. You've got, in this case, a weak base, and you've got its salt. So NH3 is the weak base. Okay, so here's your NH3. And we know it doesn't dissociate very much. So even though you will have some NH4 and some OH, they're going to be very, because it's weak, these concentrations are going to be very, very small. So we almost, for now, don't really count them. So that means that your concentration that I give you up here for NH3 is the concentration that's going to go straight into your ice chart. Now let's look at your salt. So this ammonium nitrate. I'll do that in blue. So you know it's a salt and it will completely dissolve. So that's, or completely dissociate. So if I have 1.15 molar of that, got 0.15 molar of that, and 0.15 molar of that, because it's a 1-to-1 ratio, and 100% of these molecules will separate into its ions. So for this buffer solution, I'm starting off with that concentration of my ammonium ion. But I don't know what my concentration of my OH is going to be. So for now, what we're going to do is we're going to assume this is we're going to use this ice chart. But what I like to do with the ice chart is I like to, at least for now, just ignore the C and the E columns. Because basically what we're going to do is when we add to those columns, this is going to be what happens when we add acid or base. So we're going to do an example of that after, okay? So if we add acid or base, then the equilibrium of the buffer is going to change. But for now, we're kind of just looking at, here's just the buffer. I haven't changed anything to it. Can I calculate the pH of that buffer solution? So if I do that, can I basically take this, take the Kb for NH3, and solve for OH, which in this case I'm going to call X. So here's how I do it. There is my Kb equation. Okay, in this case, I can use my 100 rule, so I can ignore any other value of X, and I get 1.8 times 10 to the negative 5 equals my initial concentrations, basically. In my formula there, I can rearrange the formula and write X. Okay, that X is the same as my hydroxide ion concentration, so I can use that and plug it in up there. Find the pOH, and from the pOH I can find the pH. As a side note, you can also solve this problem using the Ka reaction. So here's the Ka reaction for the ammonium ion, NH4+, donating its proton and becoming NH3NH+. But if you do this, you just have to take this value for Kb and first convert it to its corresponding Ka value, just like we've been doing in the last couple of videos. So that would be, to find the Ka of the ammonium ion, you'd again have to do Kw divided by Kb of ammonia. Okay, so you can do it that way. You should end up with the same answer in the end. All right, so now what we're going to do is, again, ignore all my writing here, sorry. We're going to look at another buffer solution, but this time we're going to add some acid to it later on and some base to it. So here we've got a buffer solution. Contains 0.2 molar of HCHO2 and 0.3 molar of NaCHO2. Oh my lord goodness, I can't speak. The volume of the solution is 125 mils, and Ka for the acid is 1.8 times 10 to the negative 4. Part A, what is the pH of the buffer solution? This is exactly the same as what we just did, except in this case we're dealing with an acid. So you have a salt, which will completely dissociate, and you have an acid, which won't completely ionize. So we can figure out that my concentration here is the same as what's given in the question, which was 0.30 molar. My concentration for my acid is going to be the same as what's given in the question. Okay. If you want, I can sort of redo the ice chart with respect to the buffer and just kind of show you how that works. So in this case, if your initial concentration of your HCO2 is 0.2 molar, and your hydrogen ion concentration was 0, and your CHO2 concentration was 0.30, what basically ends up happening is this goes down by X, this goes up by X, and this goes up by X. But you end up using your 100 rule and getting 0.2 minus X, X, and 0.3 plus X. Thing is when you use your 100 rule, these X's get eliminated, and you still end up with the same equation when you actually plug in your Ka. So now when I actually calculate my x, if I solve for x, there's my answer there. So there's my Ka expression. I've got my products over my reactants. And I just plug in the numbers straight from the ice chart. I find my value of x. And remember that that value of x was the same as my hydrogen ion concentration, or H3O plus concentration. So I use that number directly in my pH concentration, or my pH calculation, to find the pH of 3.92. Now if I go back for a quick second, check this out. Check out the buffer. The buffer is making some H plus ions. So I should assume that the pH for this buffer is acidic. And when I calculate the pH, it is at 3.92. All right, in my next couple of examples, I'm going to show you what happens when we add some base and when we add some acid. So in both cases, the pH is going to change a little bit, but again, because it's a buffer, we shouldn't see a drastic change. So let's do an example right now of adding some base. So we're going to take this exact same buffer and check out my question now. Oof, sorry. Ignore all this, and I will talk you through it. It's better that way. So here's the exact same buffer solution, but now I'm adding 50 mils of 0.1 molar NaOH. If that's the case, what is the pH? So we know we're going to add base, which means my pH should go up by a little bit. So it started off at 3.92. It should go up by a bit, but it should not go up drastically. So first thing I'm going to realize is that this is a strong base. It's going to dissociate completely, and my OH here is going to react with something. So the first thing I want to look at is what will it react with, and how much do I have of it to react. So I first calculate my moles of NaOH using my C times V equation. Okay, this helps me to understand what is happening in the buffer. Okay, it seems sort of simple, but it's really helpful. So I have a 0.1 molar at 0.05 liters. So I'm actually going to add 0.005 moles of NaOH to my buffer. So that's the number of moles that I'm adding. So now, you also have to understand that when you do the neutralization, your strong base is going to react with the weak acid. So in my strong base, I'm going to react. I'm going to write out the reaction. So I started out, here's my weak base, or my weak acid, sorry, from the buffer. And it's going to react with my hydroxide ions from the base, okay? I'm not putting in the NaOH, again, because it's going to end up being a spectator ion, so I just want you to focus in on the actual ions that are taking place, okay? So again, I could write, if you wanted me to, I could write NaOH, but my Na is basically just going to cancel out on both sides because it's a spectator ion. So what will end up happening, I'll have NaCHO2 and H2O. Okay, or if I take out the Na here, because it's not really doing anything, this is my sort of final neutralization reaction. Okay, so my acid reacts with my base, then makes your CHO2 and your H2O. All right, so when this happens, when I recalculate my concentrations, what am I going to see? Well, when I add my OH, now let's look at Le Chatelier's principle. When I add this, I'm going to add this, and that is going to shift the equilibrium towards the product side. So that means that my concentration of HCO2 will decrease. Oh, sorry, HCHO2, and my concentration of CHO2 minus should increase. By how much? This is all a 1-to-1-to-1 ratio. So my HCHO2 is going to go down by 0.005 moles, because that's what I calculated up here. And my CHO2 minus is going to go up by 0.005 moles. So hopefully you see that. You have to understand that concept. Otherwise, you're not going to be able to do any more of the calculations here. Oh, silly thing. There. So adding OH pushes my equilibrium to the product side and increases the reactants, but it's going to decrease my concentration of my acid, which is in the reactant side. All right, so let's go through this. So where did I start off? Before I added NaOH, I calculated my moles of this to be C times V, or 0.2 times 0.125. This is basically the information that I got from the buffer. Okay, and before I added the NaOH, my moles of this was the same thing, C times V, but in this case it was 0.3 times 0.125, so I had 0.0375 moles of my CHO2. Okay, I'm not going to look at the concentrations or the moles of the H2O, and I know how much OH I added. So when I add in this OH, I'm going to add in 0.005, and it's all going to react up. Okay, so I'm not going to have any OH minus left over, okay? But I know that this is going to, after I add NaOH, I'm going to take this moles and go down by 0.005 because it's going to react, and this one's going to increase by 0.005. So now when I calculate my new concentrations, I've got 0.002 moles of my acid. And when I add this up, I've got 0.0425 moles of my conjugate base. Now I can calculate the new concentrations, because now I can do C equals N over V. So if I calculate the new concentrations, I do C equals, there's my N, and I'm going to divide it by the new volume, which is the 50 mils from up here added to the 125 mils that I already had. So that's 175 mils. And I get my new concentration of my acid to be 0.1143, and my new concentration of my conjugate base, 0.175, to be 0.243. So what I just did there was I did my equilibrium. Sorry, I'm going to skip that. I did my equilibrium calculations for you. Okay, so if I take this out, so you're not frantic, don't frantically copy this down. I'll give you time after to do it, or you can pause it. Okay, so I basically just went through the ice chart, but I went through it in moles instead of in concentrations, just to help you understand what was going on. So now my final concentration of my HCHO2 was 0.1143, and my CHO2 minus was 0.243. I still need to find this value for H plus. So how do I do that? Well, I have the Ka for this reaction. So remember, it'll be H plus times CHO2 minus all over your HCHO2. So when I put in my numbers for that, my value for H plus is X, 0.243 over 0.1143. And your value for Ka was given to you, or you could look it up, and it was 1.8 times 10 to the negative 4. So when I do that and I rearrange and I solve for X, I see that X is 8.47 times 10 to the negative 5. And then I can use that to find my pH. And I started off, remember, if you look back at your notes, you started off with a pH of 3.92. And then you added some acid. It went up, but not by very much. So I know I did it right. That's sort of my way of checking. Okay, I'm going to start you with the next example, and I'm going to give you the final answer, but I'd like you to try it on your own to see if you can get it, okay? So we're going to do the exact same buffer, okay, but again, you're going to add base to this instead of acid. So same process, but, oh, sorry, you're adding, not base, you're adding acid instead of base, okay? So start by figuring out how much acid are you adding. So what are your moles of HCl that you're adding In this case, it's C times V. So you're adding 0.1 moles. You're adding 50 mils of it. So you're going to end up adding 0.005 moles of your HCl. I did that on purpose just to keep the numbers the same so that you guys could figure this out relatively easily. So again, find your new concentrations. So when you add HCl, what does it cause for your equilibrium shift for your buffer solution? So remember, here's your buffer solution, HCHO2. Now you're going to actually add acid to it instead of base. Oh, I didn't write that correctly. I'm sorry. So let's just write out HCHO2. If you can't figure this out, just write out your hydrolyzing reaction, your hydrolysis reaction, and figure out what happens. HCHO2 minus plus H3O plus. Okay, so here's my hydrolysis reaction. What's going to happen when you add acid? You're going to increase this. You're going to shift the equilibrium towards the product side. So in this case, your concentration of HCHO2 should go up, and your concentration of your anion should go down because the equilibrium is shifting to the opposite direction. So start by that. Find your moles of these. Same from the last example. And in this case, you're going to add 0.005 moles to that, and you're going to subtract 0.005 moles to that, and find your new volume. So that gives you, you can find your new concentration using C equals N over V. Okay. And this is going to be, again, your total volume. And this was going to be your new calculated based on how much will actually react with the strong acid. Punch those into your ice chart and see what you can get. Can you come up with a final answer? In this case, your final answer is going to have a pH of 3.78, which went down a little bit. Again, we expected that because we added some acid. Okay, so I'm going to leave you with that. See if you can get to that answer. If you can't, talk to me in class and we'll go through it step by step. And I know there is one more example in your notes, but I'm going to leave it there for you guys to start to figure out on your own. So again, follow the exact same example that I just went through with you and see if you can get that pH of 3.78 for this question. If you can, you're flying and buffers are going to be easy for you. So I hope that's the case with all of you.